Welcome. So let's start with the homework problems. So in this series I will be discussing all the homework problem that was given to you in last lecture. Also I am expecting it would be good if you are solving this problem, you can maybe scan your solution and you can mail to me. So mail is given here in the PDF. So this is the mail where you can send your solution, and obviously I would be expecting that if you could uh, send this solution before releasing the before releasing the solution of this homework problem, right? And it is up to you that, so it's not mandatory, but if you want to be continue with your preparation, then you can do that such thing. Okay, so let's start with the first problem. Okay, let's look at this first problem. So what we have been asked, that describe geometrically all linear combination of these two vectors. So basically the main point of this question is to get the idea of linear combination, and the main focus of this question is to have you the visualization of this linear combination. So if you are taking the linear combination of two vector, what space you will get, what space you will get by taking the linear combination, right? So we have been asked for all linear combination of this A, B, C. So let's first of all focus on this question number A, 1A, right? And you see that each vector has three components. Let me call it this vector V, and let's call this vector W, and this W has also three components. What can you comment on this V and W is that these two vectors has taken from some three-dimensional space. Why? Because to specify the V you need the three component. That means this V belongs to some three-dimensional space, and from there we have taken it, right? And similarly W also belongs to some three-dimensional space, and from there we have taken it. And how we are confirming that it belongs to some three-dimensional space? Because it has the three component, and we need the three component to specify this vector V and W. Now question is that what will be the linear combination of this V and W, right? So if you look these two vectors V and W closely, and if you try to find the relation between V and W, you will get a relation, right? Because you see, if you multiply, or if you take the if you do the scalar multiplication, that is 3V, then what you will get is W. So W vector is nothing but 3 times V, right? Because if you multiply the scalar multiplication 3, that is going to be component wise. So you will multiply with 3, with 2, and with 3, and what you will get is 3, 6, 9. So this W is nothing but the scaled version of this V, right? And if I ask you that plot this geometrically, so what you will do, you will take a three-dimensional space, because these two vector belongs to some three-dimensional space. So let me do that. If we can so, and we have here our z-axis, so this vector V will be somewhere here, and this vector w will be on the same line, right? So this will be vector w, and this is your vector v, and this vector w is nothing but 3 times v, and this is v, right? So now what we have to look at the linear combination of this w and v. So if I ask you how you are going to give me the linear combination, what you will do, you will simply scale the v, right? Let me use the black one. So you will scale the v vector by some constant, and you will scale the w vector by some constant, and you will add up. This is how we have defined, this is how the linear combination is defined, right? Linear combination is nothing but the combined operation, if you combine these two, scalar multiplication and addition, and if you put together, what you will get is the linear combination. So this is what we are going to get, right? And we can write c times v plus d, and this w is nothing but 3 times v, and this c and d are here, that is some real number, you can say some any scalar, any number, right? And this, so we can write this as c plus 3d times v. So this is some number, and that is getting multiplied with some vector, right? So you see that what linear combination you are getting is a line. What space of linear combination of v and w will give you is a line. Sorry, not lion but line, right? So the linear combination of v and w, in this case let me write linear combination as LC. The linear combination of v and w, the space of linear combination of v and w is a line in R3, right? And in last video we have discussed this what is this notation R3 is, right? So now this solves our problem. So this is A. Now let's look at this B, right? So this B, again we will have, so can you find any relation between let me call this vector v and u? Can you find any relation between vector v and w? We cannot find it, right? You will not find, because both those vectors are in different direction. And how I am saying that, right? This should be your question. Let me call it this vector v, and let's call this vector w, right? Why I'm saying that we, in this case we have found some relation between v and w, but if you look at this vector v has the x component, right? But this vector w has no x component. This vector v has no y and z component, but this vector w has y and z component. So this v and w is completely different direction, right? We will in further videos we will be talking about the independent. I am not introducing these terms right now because we will be going through these terms, because this v and w are independent vector, right? But let me not use this word right now. So these two vectors are in different direction. So this v, let me say that this is x-axis, this is y, this is z, then this v have no y and z component, so that is going to be maybe this vector v, right? So this is vector v, and this vector w is somewhere maybe with 2 and with maybe 3, so that will be in zy plane, and that will be this one maybe, right? Now the question is the geometry of linear combination of v and w, how it is going to look like, right? We saw in this case, right, the geometry of linear combination of v and w is a line in three-dimensional space, right? Now in this case you see that this is our vector v, right, and this is our vector w. So, and both these two vectors are in both different direction. So if you take and if I am asking the linear combination, what you are going to do, you are going to give me the linear combination of v and w. So what you are going to do, you are going to simply multiply multiply v with some scalar c, and multiply w with some scalar d, and you are going to add up, and you are going to give me this one, and you will tell this is the linear combination of this v and w. So let me write it down. So that is v is a 1 0 0, and this w is d times 0 2 3, right? So what we are going to get is c and 2d and 3d, right? So you can pick any value of c and d. So what you will get is a plane, right? You will get a plane that will be passing through the origin, because you can take the value of c as 0 obviously, and d as 0, right? So c and d is 0, then this vector is going to be 0, right? And so what are the vectors that is going to reside on this plane that is described by the linear combination of this v and w? So you can look at this one, and you can say, you can pick any c. Let me pick at c1 and d as 1. So 1 2 3 will be a vector that is going to be on the plane described by the linear combination of this v and w, right? So in this case we will have some kind of plane. So let me draw, maybe if I can draw. So we will have some plane, right? So, and what are the vectors that will be, there will be infinite number of vectors that will be going to be on the plane described by the linear combination of this v and w, right? So you can pick, so okay, so the space of linear combination of v and w is a plane in R cube. Okay, now let's come to this part C, right? And if, let me give it a name, VW, maybe UVW. Let's give it as a name UVW. So these are the vectors, and you see that this vector u that have no y and z component, and it has some x component, and this v is this v have no x component, but it has y and z component, and w has all the components, right? That is non-zero. So you can look at this u, v and w, and you can say that these all all these three vectors are in different direction, right? Or you can say these are the independent, but let's not use this word independent. So these three vectors are in different direction. So if you draw these three vectors in maybe with this, so that will be all will be in three directions. So this is maybe this is u, and this will be v, and z is going to be maybe somewhere here, and this is u, right? And what will be the linear combination? So what you will do, you will simply multiply the scalar with v, multiply the scalar with u and with u and v and with w, right? So you are going to do this d times, this is w, right? And d times v and e times w, and you are going to add those, and you will say this is the linear combination of this vector u, v and w. So what you will get is this plus d times 0, 2, 2 and plus e times 2, 2, 3. So that is going to be 2c plus 2e, 2d plus 2e and 2d plus 3e, right? So in this case, the space of linear combination is entire R cube, right? So let me summarize this one. So you can pick any value of c and d, and in this three-dimensional space you are going to be only on this line. You cannot go beyond on this line, right? So you can pick any value of c and d. You will be not exploring beyond this line. You can explore your space with this any value of c and d onto this line, right? And this line can be from minus infinity to plus infinity, right? And this case of b, with any value of c and d, you are going to stay on this plane, and this plane again could be from plus infinity to minus infinity. So you can explore only this plane, and you cannot again explore the complete three-dimensional space. You cannot reach each and every point of three-dimensional space. What can you get is each and every point described by this plane, right? And in this case c, you will be with the combination of this particular vector u, v, w. You can, by picking a particular choice of c, d, e, you can explore each and every point of this three-dimensional space, right? So this summarizes this question, and I hope it makes sense to you. Now we will be moving to next question. Okay, so that was your second question. So let me explain this. So compute u plus v plus w and 2u 2v plus w. How do you know that u, v, w lies in a plane, right? And if you look this u, v, w, all those have 3 components, that means definitely these vectors are from some 3-dimensional space. But combinedly these 3 vectors, and it is given that how do you know that this lies on these 3 vectors lies on a plane. So even if you are taking their linear combination, these 3 vectors have the capacity only to explore only the plane, not complete 3-dimensional space. Okay, so let me tell you here one thing, that by so in first question, how you were able to see that this w is 3 times v, right? It was directly visible, right, from this given vector. So that is one case, and here it may happen that you will not be able to directly see that some vector is some multiple or some kind of combination of other thing, and if you take the combination of something, that will be producing something. So let me not confuse on this. So let's stick to this question, and you will get to know what I am saying. That so first of all, compute u plus v plus w. I am not going to compute that. And 2u plus 2v plus w, or let me compute that. So let's first calculate this u plus v plus w. So what we are doing, we are again taking a linear combination, but with a particular choice of CDE, right? This is nothing but 1 times u, nothing but 1 times v, nothing but 1 times w. So this will give you a specific combination, right? This is not going to give you the complete entire combination, right? For that you will have to take CDE, but we are picking a specific value of CDE, right? So that will be so let me use the black color. So 1 2 3 plus v is minus 3 1 minus 2, and this w is 2 minus 3 minus 1. So what we are going to get is 0 0 and 0, right? So you see that with this value of their c is equals to d is equals to e is equals to 1, if we are taking the combination with this particular value of CDE, that is 1, what we are getting is a 0 vector, right? Now let's calculate this one, 2b, and so this 2 times u plus 2 times v plus w, that will be 2 4 and 6 plus minus 6 2 and minus 4 and plus 2 minus 3 and minus 1. So what we will be getting is 2 plus 2 4 and minus 2, and 4 6 minus 3 is 3, and here we have 6 minus 5 is 5, sorry, 6 minus 5 is 1. Right, so you see here we have taken some specific value of the CDEs, that c is equals to 2, d is equals to 2, e is equals to 1, right? And we are taking the linear combination, and what we are getting is this, right? So how do you know that this u, v and w lie in a plane. So we have given this 3 vector, and so what I can say, if these 3 vectors lying on a plane in a 3-dimensional space, then there would be a vector that would be linear combination of some other 2 vector, right? This point, let me tell you one more time that if these 3 vectors are lying on a plane in 3-dimensional space, then we can guarantee that one of these 3 vector is a linear combination of other 2 vector, right? So if it is not directly visible to you, do not worry about that. We have lot of methods to find this if a vector is a linear combination of other 2 vector. You will see further videos that we have the lot of other ways, like calculating the determinant. I do not want to introduce all these things, right? But we have lot of other ways to find this particular thing, that something is a linear combination of other 2 thing or 3 thing, right? So in this question we have also given that this lies in a plane because W is a linear combination of u and v. So this vector W is a linear combination of, but for what particular value of C and D you will get this W, right? That we have to find C and D. Okay, so we know that W is a linear combination of, so W is a linear combination of V or U comma V, right? So in question 1 you see that all these 3 U, V, W were in different direction, right? But here what is happening, that these 2 U and V are in different direction, but this W is in the plane described by this U and V, right? So what we have to find is simply C and D, right? So, and it is given as of now in the question that W is a linear combination of this C is this U and V, right? So we can write this W. So W is equals to C U plus dV, right? So for what value of C and D will give you this W vector, right? So you see that if we have this vector V and W, we can have a specific value of this C and W, and we can get this kind of value, this kind of vector, right? We can get this vector. So depending on the value of C and D, but what we have given that, let's suppose you have this vector, right? So what value of C and D will give you this vector? That is what we have to find, right? So we can write this W, that is 2 minus 3 1, and C and U is 1 2 3, and V is minus 3 1 minus 2, right? And we can do the scalar multiplication, right? So that will be C plus C minus 3D, right? We will do the multiplication and we will add here. So C minus 3D is equals to, that should be component wise equal, that is 2, that is one equation, and 2C plus D is equal to minus 3, and 3C minus 2D is equal to 1, right? So these are the 3 equations that you can solve, and you will get the value of, even we do not need to solve these 3 equations. What we can do, we can right? So let's solve this. Maybe we will get to know more what it is saying. That so we can solve this equation 1 and 2. So we can multiply this equation 2 by 3. So we will have c minus 3d is equals to 2, and this equation 2 is 6c plus 3d is equals to minus 9. So this will get cancelled. So 7c is equal to minus c, and from here we have c is equals to 1 minus 1, right? And we can put this c in equation first. So minus 1 minus 3d is equals to 2, and from here what we will get is minus 3d is equals to 3. So d is equals to minus 1. So what value of c and d you will have this vector? So c is equals to minus 1 and d is equals to minus 1. So if we put this c and d into this 3, we will have, okay, so this w is here minus 1, right? So here we have minus 1, here we have minus 1, so minus 3 plus 2 is minus 1, right? And if you see that this addition tells you something, that u plus v plus w, and what we are getting is 0, right? So here u plus v plus w is 0. So from here what we can write is u plus v is equals to minus times of w, or we can, so what it is telling you, that this w is nothing but minus times of u or v, or if you add this u or v, what you will get is minus times of w, right? So let me do that. So if you add 3, if you add this 1 minus 3, what you will get is minus 2, and minus times of minus 2 you will get 2, right? And if you add this 2 plus 1, that is 3, and minus times of 3 will be minus 3, right? And similarly 3 minus 2 is 1, but minus times of 1 is minus 1, right? So what it is telling you, that this w is nothing but, you can say, is the linear combination of this u and v, right? So the main point here to take is that we have here two vectors that are in different direction, or you can say these two vectors are independent, and this w is dependent on this u and v, right? Okay, now let's move to next question. That was the third question. Every combination of v and w has components that adds to, so every combination of v and w has component that adds to, so what we have to add is the components of v and w. So every combination of v, how you can take the every combination of v, right? So let's suppose that v, you have v, right? So you can take the combination of v with by multiplying this c, right? Any number, and that will give you some c minus 2 times c and c, right? The point is that if you add the components of v, right, what you will get, so 1 minus 2 1. So by adding the component, what you will get is 0 each component, right? So even if you take the combination of this v, right, so this will add up to 0, right? C plus c, 2c, and minus 2c, that will 0, right? So if you add the components every combination of v, then you will end up with the 0, right? And for w, if you take maybe with the dw, so dw, that would be, and if you add, what you will get is 0, right? In this case also, so d times of g, that will be 0, d and minus d, right? So every combination of v and w has component that adds to, and if you take the every combination, and we can do the plus, and what you will get is c minus 2c plus d and c minus d, right? And even if you take every combination of v and w, and if you add these component, what you will get is c minus 2c plus d plus c minus d, that is going to be 0, right? So question was every combination of v and w, so we have taken the each and every possible combination of v and w has this component, and if we add those, so if we add those component, what we will get is 0. Now we have next part in this question, find c and d so that the linear combination of this v and w will produce this vector. So what value of c and d is going to give you this vector, right? So we can look at this as usual. What we can do, we have c, right, and v is 1 minus 2 1, and plus we have d, and w is 0 1 minus 1, and this particular combination should give you 3 minus 6, right? So we can do, so here we will have 2 minus 2c plus d, and here we have c minus d, and this should be equal to 3 3 6. And if these two are equal, that means their component needs to be equal, right? So here we will have c, right, because c times 1 is c, so their component needs to be equal. So from here what we can write is c is equals to 3, right? And if we put here c is equals to 3, so we will have minus 6 plus d, and that should be equal to this component, that is 3. So d is equals to 9, right? And if we have 3, and here if we have d9, that will give you minus 6. So we are good with that, right? So you can check it, you can directly put here c3 and d9. So what we will get is 3, right, and minus 6 plus 9, we will get 3, and 3 minus 9, we will get minus 6. So we are correct. And now question is that why 3 3 6 impossible? That the question is asking that if we are taking this particular combination, can we get this 3 3 6? Can we get this 3 3 6? And why it is not possible to get 3 3 6? So the point is here, that so in first part what we find, that if you take any combination, any linear combination, and if you see that we have add up the component of this, right, and what we have found that it is 0, and we have add up this component of w, what we found that this component is also 0, and we took the linear combination of this v and w, and we found the components of linear combination of v and w, and we add up those components, and we found that it is 0, right? And if you see here, this side, that right hand side, this component, if you add up these component, that is 3 minus 6, that will give you 0, right? So, and if you add this right hand side component, so left hand side, that is also going to give you 0, right? So 0 is equals to 0, right? And why this is impossible? Because if you see the right hand side, we have the right hand side, that is 3 3 6, and if you add the component of this, and in the left hand side, even after taking the linear combination, the component addition of the component is 0, but you see here the addition of this components are not equals to 0, right? So so that is why this combination is not producing this particular vector, right? And one more way to see this, that the linear combination, whatever the linear combination of this C and W, that would be a plane, I think, that is not going to, so that plane will not have this vector. So this vector will be outside the plane that is spanned by the linear combination of this V and W, right? I think that is all about this question number 3. Now let's move to next question. So this was the 4th question of your homework, right? So let's look at this. So in XY plane, mark all 9 of these linear combination with C is equals to this and D is equals to this. You see that here C have some constraint, or you can say C have some, but some value, that is 0 1 2 only, and D has only 0 1 2. So this, even if you are not able to still completely grasp the linear combination what it is giving, so this question is good, you can say at a small level, to visualize the linear combination, because with lot of values of C, or with the continuous value of C and D, it may like difficult to see the picture, but with a small value of C and D, even in last video I have taken a problem where C is a whole number, C is a number that is greater than 0, right? And if you see that in last video, that what kind of space that linear combination of vectors are giving to us. Okay, so we have given this linear combination already, right, of this vector, some vector V, let's call this vector V, and this vector W. And so first of all, the question is that with this value of C and D, how many points in this 2-dimensional space we are going to get, because these two vector belongs to some 2-dimensional space. So these two vector may explore the entire 2-dimensional space, that we have seen that kind of example. They may explore a line in 2-dimensional space, that kind of example also we have seen. And they may even explore a point, or 2 point, or 3 point, or maybe 9 point, or 10 point in a 2-dimensional space. And that depends on this value of C and D also, right? So if we have this is C and D, that is 0 1 2, and D is equals to 0 1 2, then what are the points? Because I'm talking in this case, we will be getting points, even we will be not getting any line, or we will be not getting any plane, right? So let me first of all draw this 2-dimensional space, because our vector V and W belongs to some two-dimensional space, right? So what we can do, we can vary, we can pick c is equals to 0 and we can vary d, right? So so what we will be getting, we will be get c is equals to 0 times 2 1 plus we can pick d is equals to 0, so so we will be getting 0 0 obviously, right? And c is fixed, we are fixed, so fix c is equals to 0 and vary this d, so we can fix c is equal to 0 and we can pick now d is equals to 1, right? So what we will be getting is 1 0 1. So again here we will have 0 times 2 1, so we are fixing c and varying this d, so we will get 0 2, right? So by doing this, what are the point we are we will get? So let me first of all mark this 1 2 3 4 and 1 2 3 and 4. So first of all we will be getting this 0 0, right? Here with c is equals to 0, d is equals to 0, we will get this particular point. And again with c is equals to 0 and d is equals to 1, we will get 0 1, so we will get this point. And with c is equals to 0, d is equals to 2, we will get this point, right? So these are the points that we will be getting, and now we can change the c to 1 and again we vary d, so we can pick c is equals to 1 4 2 1, and again let me write all of them, and we can vary this d, so we can pick this d as 0 and we can pick this d as 1 and we can pick this d as 2 also, right? So from here what we will get is 2 1, right? And from here what we will get is 2 and 2, and here we will be getting 2 and 3, right? If I am not wrong. So what are the point we will be getting is 2 and 1, so this point, and 2 and 2, this point, and 2 and 3 and this point. See how we are reaching to different point by changing the value of c and d. Now think, if c belongs to some real number and d belongs to some real number, and we have this vector v and this vector w. Now think in two-dimensional space where you will be reaching. You will touch each and every point by choosing the value of c and d. If you want to reach 2 1 1, let's pick c and d this value and you will reach that particular point. You may wish to reach at any point by choosing the value of c and d, right? Now let's come to our question. Now we can vary again c, we can fix c to 2 and we can vary this d to any 0 1 2 3. So 2 times we will have 2 1, again 2 times we will have 2 1, 2 times we will have 2 1 and plus 0 times we will have 0 1, and 1 times we will have 0 1 and plus 1 times we will have 0 1. So from here what we will get is 4 and 2, and from here we will have 4 and 3, and from here we will have 4 and 2 2 plus 1 3, same. So it is here, we will have 2, right? So we will be getting 4 and 4. Right, now let's draw what are the points we are getting. So 4 2, so this is the first point, and 4 3, so this is the second point, and 4 4. So 4 4 is somewhere here. All right, so these are the points, and if you want to look at in terms of vector, so this is the first vector at 0 0 that we are getting, and this is the second one, this is third, and this is fourth, and this is fifth, 6 7 8 and 9. So with this particular choice of C and D, and with this vector V and D, and if we take the linear combination with this choice of V, W, C and D, we will be reaching to these points, not more than that, right? In two-dimensional space, with this V, W, and with the choice of this particular choice of C and D, we will be exploring these pink points, not more than that. Okay, so this is question number 5 from your homework, and I should say that you should try this question. So again, it will give you a picture of linear combinations, right? So if you take this C, that is from 0 to 1, and D, that is from 0 to 1, then what kind of space that will be given by the linear combination of this CV plus DW, right? So you will have idea that if I am restricting this C and D value from 0 to 1, then what kind of space you will get. So let me just go through one. So you see that if you take C is equals to 1, and so if you take this V plus W, right? So you will do the addition of these two vectors, right? So how you can do that? So you can simply shift this W to the tip of this V, and this V to the tip of W, right? So with this particular combination with C is equals to 1, D is equals to 1, you are going to get this point, right? Now if you vary this C, right, now C is from 0 to 1 and D is from 0 to 1. So what kind of space you will get? So I can say you that now, since you are taking some C that is less than 1 or greater than 0, let's suppose you have taken this point, so this vector that is from W, and this vector from maybe with V. So now you add these two, so again you will have this parallel to this and this one. So what point you will get? This one, right? So you take each and every point of C that is from 0 to 1, and you take each and every value of D, and then this linear combination, how it is going to be look like is this line, right? So you will get this one. So on this line you will be able to get each and every point on this line, right, by varying this C and D and taking the linear combination, right? So this kind of questions are there, so you will have idea what space is going to be acquired by the linear combination of this v and w with some constraint with the value of c and d, or maybe with the so it depends on this c and d, that what space you are going to get, and also it depends on this vector v and w. So you should definitely try this question number 5. I'm going to skip now this question, right? And you should try this one, because ultimately you will have to see that the picture of this linear combination. So try this question, and even if you have difficulty, let me know. I will make a separate video for the all these questions, so you can try this question number 5 and 6. Then you will have the good visualization of this linear combination. Okay, now with this let me wrap up the first subtopic of our topic, that is introduction to vector. So now we will wrap up this vector and linear combination. So from my side we are done with this chapter, and if you have any problem, any question related to that, you can write me on this mail, or you can comment on any of videos. I will go through that and I will try to resolve that doubt. So from next video we are going to start with our next topic, that is length and dot products, and we are not going to spend that much of time as we have spent it on this linear and linear combination, right? So that is all from this video. Thank you.